Gnanam Paramam Dheyam. Knowledge is supreme.
So, in the last lecture, we have seen the connection between the degree of the field extension and the order of the Galois group. So, let me recall briefly that we are in this course we are studying field extensions with the help of groups, and for arbitrary field extension L over K, this field extension, the group we are talking about is the Galois group, Gal L over K. This group is precisely the automorphisms of the field L as K algebra. L is a field over K, therefore L is thought as a K algebra over K, and we are looking at the automorphisms of that algebra, and that is clearly a group because composition of automorphisms is again automorphism. So, it is a group under composition. In fact, this is a subgroup of S of L, the permutation. These permutations of L is a very big group. They are only bijective maps from L to L. And automorphism are particular bijections, namely they are the one which preserve the addition and multiplication, and also 1 goes to 1. So, this group was first considered by Galois, and in the whole course we are going to study field extensions by using this group, and this intimate connection is precisely called the Galois theory. And what did we prove so far is, this was a theorem we proved. This was the order of the Galois group is bounded by the degree of the field extension. And this theorem we proved under the assumption that L over K is a finite extension, finite field extension. That is because this side should make sense. A degree of L over K should make sense. So, therefore, we need finite field extension. Alright. So, and we defined extension to be Galois extension, L over K Galois extension, if the equality holds. And after that we have seen some examples which also shows that the Galois, and we analyze the simple Galois, when a simple extension will be Galois extension. That was what we have analyzed, and that is if and only if the minimal polynomial splits into distinct simple linear factors in L. So, that means all roots of the minimal polynomial of this generating element should lie in L, and they are different, there are no repeated roots. So, that was what we have checked, that is how simple extensions are Galois. Now, today I want to also little bit tell some more general comments about this philosophy, that for example, to each object, this is to each object we attach a group. For example, to a set is an object. See, this object concept can be made more careful with the definition of categories, but we do not need in that generality. So, I will just explain you by examples. For example, sets are objects. So, when one studies set theory, we compare two sets. Also, we study the maps between them. We study different kinds of special maps between them, namely injective maps, surjective maps, bijective maps, and so on. So, to each set, we have attached a group called the symmetric group of X, Sx. They are precisely bijective maps from X to X. Now, instead of set, if I had a group G, I would attach not only all bijective maps, but special kind of bijective maps, namely the bijective maps which preserve the group structure. That means bijective maps which respect the group structure. So, those are precisely called the automorphisms of G, and then a group. So, I will not write that is suffix here. It is understood that when I write odd G, when G is object, this is a group. These are precisely group automorphisms, and that is clearly a group. It is a subgroup of S of G. Similarly, if I had more, if I had say monoid, before that I should have said if M is a monoid, then odd M is automorphisms of monoid. Here little bit we have to be careful that we need to assume that monoid homomorphisms maps identity to identity. That is not a consequence in general, unlike groups. Similarly, if you have a ring, R ring, then we have odd R. To be very clear, one usually writes here rings. Similarly, he will write groups and so on. So, more generally, if you have a module over ring R, R mod, R module, then we have automorphisms of that module M as a R module. So, R linear maps which are bijective. So, this is also a group. So, if you have a vector space K, if this is a particular case of the above example, if K is a vector space, then we have odd vector space V, then odd V over K, this automorphism. So, each object we have a automorphism group of that object. For example, the one we were interested in, the field extension, L over K field extension, then we have these automorphisms as a K algebra. This is precisely the group we want to study more carefully. We could have also done, if you have a field L, then aut L, just automorphisms of the field. And philosophy is, from the knowledge of the automorphism groups, you get the knowledge of the object and conversely. So, this interplay is very, very important in mathematics, and one does not stop here. We can go on, topological space, homeomorphisms, differentiable manifolds, differentiable maps, and so on. I will not go much into that. What I want to say that when the two definitions I want to make. When do you call an object symmetric? Object is called symmetric if the automorphism group of that object, let us call that object to be X, automorphism group of this object X, this should be maximum possible. Maximum possible. This is little bit vague, but I will make with examples more clear. And the elements of this automorphism group are called the symmetry of that objects. Elements of aut X are called symmetries of X. For example, what we proved that the cardinality of this automorphism group of the field extension can at most be the degree of the field extension. So, these are the symmetrics of the field extension, and when will it be maximum? When the equality holds here, and that is precisely what are called Galois extensions. So, Galois extensions are the most symmetric field extensions with this definition. So, similarly other objects. So, these are the symmetric objects, and opposite of that is what are called rigid objects. So, objects are called object X is called rigid if the automorphism group is a trivial group, just identity of X. Identity of X is clearly an automorphism. So, automorphism group is a trivial one, that is, then the object is called rigid. That means there are no symmetries of X other than the identities. Now, one can ask various questions. Can one characterize rigid sets, rigid groups, rigid rings, rigid automorphisms, rigid field extensions, and so on, or rigid fields? Or you can also keep asking ordered sets. Ordered sets are also objects, and symmetries of the ordered sets are precisely the order preserving maps which are bijective. So, all these questions will come up. How do you say that the objects are symmetric? Characterization of orders, objects which are symmetric and which are rigid. These are of very prime importance in studying in any subject, and in this course we are only studying the field extensions which are symmetric, and they are Galois extensions, and how do we characterize them and so on. So, we are studying Galois extension, and that is why this is called Galois theory. So, for example, I want to remind, example last time we have said is automorphisms of R as a field at R. This is a trivial group. This needs a proof. So, I will just here check. This is, therefore, R is a rigid field. R is a rigid field, because the only automorphism is identity. More examples of rigid fields are, for example, if you take the prime fields. Prime fields are precisely Z mod P, where P varies in prime numbers, and Q. These are rigid fields. These are for each characteristic there is exactly one prime field. That means, if K is a field of characteristic P, then it contains Z mod P, and if K is a characteristic of 0, then it contains definitely field Q. And therefore, with this also we know, because we are considering if K is any field, and if I just take aught K, automorphisms of the field K, that is same thing as automorphisms of the field K over the prime field. So, let us call, so if K has characteristic P, then it is Z mod P. If characteristic K is P, positive. If it is 0, this is aught K Q algebra, I should say, Q algebra. Because they are automatically, if characteristic is P, every automorphism will automatically be Z mod P linear, because Z mod P is generated, additive group is generated by 1. So, once you know 1 goes to 1, then you know where the sum goes and so on, and everybody know all the elements are going to themselves, so they are ZP linear. Similarly for Q. So, automorphisms of a field, if I just take aught K as field, that is same thing as aught K Z mod P algebra or aught K Z mod Q algebra, depending on K is characteristic 0 or P. Alright. So, also remember I will raise this question now, but the answer we will answer later. So, for example, if I want to know what is OUGHT C, OUGHT C is therefore OUGHT C as a Q algebra. This is same as OUGHT C by the above remark, and I explained you what is the OUGHT C as R algebra homomorphisms. So, that means there are linear. So, and this is precisely two elements, one is identity map of C and the other is sigma, which is a complex conjugation. This is complex conjugation. This is what we proved last time, and this is clearly contained here because R linear will imply Q linear, but I want to stress here that this is not equal. In fact, this has cardinality 2. This group is very big group and this is even uncountable cardinality. This is a big group. And to write the elements explicitly will not be possible unless we have to take methods from transfinite sets, etc., which with the help of what is called a transcendence basis of a field extension, with that help we can describe this group. But right now we do not have those machinery to describe this group. All right. So, we continue our examples, few more examples of non-Galois extensions. So, examples. So far, remember, we have C over R is a Galois extension. Also, we have checked that finite extension of a finite field is always Galois extension, and in this case the Galois group is cyclic and generated by the Frobenius map. I just want to recall, we have proved that if I have a simple extension L, simple means generated by one element, and algebraic extension. So, whether I write round bracket or square bracket, it is same over K, finite extension, finite field extension, and then we have analyzed then for this this generator of L as a K algebra, this X, we have the minimal polynomial. This minimal polynomial is a monic polynomial with coefficients in K, and mu x of x is 0. It is an irreducible polynomial because mod ideal generated by that is precisely this field L. Therefore, it is a non-zero prime ideal and therefore, it is irreducible. So, we have proved that L over K is Galois if and only if mu x splits into simple linear factors in Lx. So, that in other words, in the notation, if I take the 0 set of mu x in L, this is the 0 set of mu x in L, this has cardinality equal to degree of mu. That means this has two conditions, that means all roots are in L and all are simple. Right. So, I want to give examples so that if any condition fails, there are two conditions here, namely the roots are simple and all roots lie in L. If any one of these two conditions fails, then the field extension is not Galois. I want to see these examples explicitly. So, first example, let us take now a rational number A. A is a rational number, non-zero, and also take any natural number n, odd. And now I look at the polynomial x power n minus a. So, this is a polynomial of odd degree. So, odd degree polynomial, and it has rational coefficients. Therefore, it has the real coefficients, and therefore, we know from our college study that this polynomial definitely has one real root. So, let small x be in R such that it is a 0 of this polynomial means small x power n equal to a, and I want to choose now a carefully, so that this x is not in Q, and that how do I make sure that will mean that this rational number. So, this is equivalent to saying the rational number, the prime decomposition of this rational number a does not have all the p exponents for the primes occurring in the prime decomposition of a, they cannot be all divisible by n. So, simply in the notation this is equivalent to saying there exists a prime number p with Vp of a is n does not divide this. And what is Vp of a? This is the pth exponent occurring in the prime decomposition of a. This is the pth exponent occurring in the prime decomposition of a. It can be a negative integer. So, I put that you will see why I put this condition, but now the situation is I am considering a field extension now Q of Q. Q is contained in Q round bracket X. Remember, whether I write round bracket or square bracket, it is same because it is a finite field extension. X is algebraic. This is X is algebraic over Q. So, I will not repeat again and again, few times it is good to repeat. Okay, so, I have a field extension, and note that because I have chosen x as a real number, this Qx is already contained in the field R. Alright, now I want to check that whether this Qx over Q, this is a simple extension, I want to check this is Galois or not. And our observation shows that if I want to check this, I should check that all the zeros of the minimal polynomial should lie completely inside this field. That is first condition. And not only that they should lie here, but they should be all distinct. There should not be any repeated zero. Okay, so but let us see how many zeros lie in. So, therefore, we are interested in the number of zeros of Q in Q, not Q, in Qx of this polynomial mu x. And what is the minimal polynomial of mu x? Whatever it is, mu x is the minimal polynomial, and because mu x is the smallest degree polynomial that x satisfies over Q, and one polynomial is definitely I know this. So, this polynomial x is the root of this polynomial. So, therefore, this should divide this where in the polynomial ring Qx. So, therefore, whatever the 0 of mu is, that will also be 0 of x power n minus a. So, that shows that this 0 set is contained in therefore V Qx of x power n minus a. So, I should know what are the zeros of x power n minus a, but well this 0 set is also contained in V C x power n minus a, and these 0 set are precisely, I am going to write down this 0 set, this is precisely x is obviously one of them, and then zeta x, zeta square x, zeta power n minus 1 x. What is zeta? So, let me remind you, we have also discussed that if I take the polynomial x power n minus 1, the roots of this polynomial in complex numbers, this is precisely the roots of unity, and we have checked that this is a finite subgroup of C cross, and therefore it is cyclic, and therefore it has a generator, and that generator is called primitive nth root, root of unity, and that is therefore this group is, this 0 set is nothing but 1 zeta and so on up to zeta power n minus 1. They are precisely n because this polynomial x power n minus a has simple roots, because when you differentiate it, the roots are not so. Therefore, this 0 set is precisely contained in this set, and on the other hand we know these are all real. They are all contained in Qx, and Qx is contained in real numbers. Therefore, we are interested only in the real zeros, but only real 0 among them is x. So, therefore, that proves that this set is only singleton x. So, therefore, minimal polynomial cannot split into the linear factors in Qx unless mu x is x only, but that cannot happen because x is a real number. This does not have a the condition. Why did I put that n does not divide Vp of a? Because I wanted a non-rational real root. So, therefore, mu x, degree mu x is definitely more than 1, and this 1 is the cardinality of the 0 set of this minimal polynomial of mu x in kx. Therefore, the condition, one of the condition is not satisfied. Therefore, as a conclusion, we conclude that Qx over Q is not Galois, extension. And in the later half, I will give another example where actually the minimal polynomial has all the roots lie in the field, but some of them could be repeated root, and therefore, the extension cannot be Galois. So, this example we will give it in the later half. So, thank you.